Welcome to this explainer. If you've ever driven past one of those massive, towering cooling plants and wondered what exactly is going on inside, well, you're in the right place. Today, we're stripping away all the mystery and looking closely at the nuts and bolts of how nuclear reactors actually function, using a breakdown straight from the Department of Energy.
So, let's start with the big question. How exactly does splitting an invisible atom end up powering millions of homes? Well, at its absolute core, nuclear power operates on a principle that is remarkably familiar. It is, in essence, the world's most advanced, high-tech tea kettle. Seriously, the entire goal of all this incredible engineering is simply to boil water, create steam, and spin a turbine. But as you'll see, the way it generates that heat is where things get truly fascinating.
It all starts right here, with nuclear fission. That's the physical process where atoms split apart. And when they do, they release just a tremendous amount of energy and heat. To put that energy density into perspective for a second, a single uranium pellet, literally the size of a gummy bear, contains as much energy as a whole ton of coal. It's mind-blowing. We aren't just burning fossil fuels here, we are literally cracking the fundamental building blocks of the universe to generate that heat.
And right now, there are actually more than 400 commercial nuclear reactors operating worldwide today. This isn't some experimental, fringe science. This is a foundational pillar of global energy, quietly and constantly undergoing nuclear fission to keep the lights on for hundreds of millions of people all around the globe.
Okay, bringing it a bit closer to home, of those 400-plus reactors globally, 94 of them are located right here in the United States. These 94 commercial reactors provide a massive chunk of the country's electricity. They serve as one of the largest sources of reliable, affordable, and secure power available to us. Rain or shine, wind or no wind, these reactors are out there splitting atoms and boiling water. All right, Section 1, inside the reactor core. Let's look at building the engine piece by piece.
So the incredible modular design of a reactor starts very small. The fuel used here is uranium. First, this uranium gets processed into these tiny, solid ceramic pellets. Next, those little pellets are stacked end-to-end inside long, sealed metal tubes called fuel rods. Finally, typically more than 200 of these individual rods are bundled together to form a fuel assembly. So it's really all about stacking, right? From tiny pellets to rods to massive bundles.
Now, when you bring a couple hundred of those fuel assemblies together in one place, you've just formed the reactor core. And the crucial detail here? They are completely, totally immersed in water inside the reactor vessel. Just picture it. You have hundreds of assemblies made up of tens of thousands of fuel rods, packed with literally millions of tiny uranium pellets, all sitting entirely underwater. Now, you might be wondering, why all the water? And how do we keep this massive reaction from getting completely out of hand? Well, the water serves two vital purposes. First, it acts as a coolant, carrying all that intense heat away. Second, it acts as a moderator. It basically cushions and slows down the neutrons produced by the splitting atoms, which is absolutely crucial to sustain the chain reaction. Then you have your control rods. Think of these as your brakes and your accelerator. Insert the control rods into the core, and they absorb neutrons, acting like brakes to reduce the reaction rate. Pull them back out, and the reaction speeds right back up. It is a perfectly beautifully balanced system.
Moving on to Section 2, light water reactors. Here are the two main types of U.S. plants.
So all commercial nuclear plants in the United States are what we call light water reactors, meaning they just use regular water as both that coolant and moderator we just talked about. But they actually operate in two entirely distinct ways. The U.S. fleet is essentially divided into two camps. The majority, over 65% of American reactors, are pressurized water reactors, or PWRs. The remaining balance, roughly 35%, are boiling water reactors, or BWRs. Let's break down what makes these two systems so totally different from one another.
Okay, let's dive into the big one first. Pressurized water reactors. And honestly, the name kind of gives the game away here. In a PWR, water is pumped into the reactor core, but it is kept under immense, crushing pressure. This extreme high pressure physically prevents the superheated water inside the core from actually boiling. So it gets incredibly, insanely hot, absorbing all that heat from the fission process, but it stays completely in a liquid state.
But wait, if the water doesn't boil, how on earth do we get the steam we need to spin our turbine? Well, it's a seriously ingenious workaround. Step 1, that superheated liquid water from the core is pumped into a heat exchanger. Step 2, this hot water flows through tubes that are surrounded by a completely separate water source. Step 3, that separate secondary water source absorbs the heat and becomes steam. And finally, Step 4, that newly created steam goes on to spin the turbine and generate our electricity. The massive fundamental takeaway here is separation. The water touching the actual radioactive core never ever touches the turbine.
All right, now let's shift gears to the other third of the U.S. fleet, boiling water reactors. Now this system is much more direct. In a BWR, water is heated to produce steam directly inside the reactor vessel itself. There is no separate loop. There is no high-pressure trick to keep it liquid. We are letting the heat of fission boil the water right there inside the core.
So in a boiling water reactor, water gets pumped straight up through the core. The intense heat from the fission turns it directly into steam. Pipes then feed that steam directly to the turbine to produce electricity. Finally, the unused steam is captured, condensed back into liquid water, and routed right back into the core to start the whole heating process over again. It's direct, it's efficient, and it's completely cyclical.
And that right there is the fundamental mechanical difference between the two technologies powering our grid. On one side, you have the PWR, relying on intense, high pressure and a completely separate secondary water source to safely generate steam. On the other side, the BWR just goes for direct steam production right inside the reactor vessel itself. Both use the incredible heat of splitting atoms, both use regular light water, and both spin huge turbines to give us electricity. But their plumbing, their entire engineering philosophy, takes two different, truly brilliant paths to get there.
So, we've traced this absolutely incredible journey. We started with a microscopic splitting atom, zoomed out to tiny ceramic pellets and towering metal assemblies, and went all the way to a spinning turbine that powers entire cities. With over 400 of these reactors currently operating worldwide, providing incredibly reliable, steady baseload power rain or shine, it leaves us with a pretty big question to ponder. How will nuclear fission continue to shape our future energy security?